Welcome students, welcome to the next session of structural analysis 2. So in the previous class we have started what are the terms involved in the flexibility matrix, what are the terms involved in the stiffness matrix. Simply in case of flexibility matrix, when I am indicating it with delta ij, or the matrix I am indicating as flexibility matrix, and this delta ij is indicating what? It is indicating displacement developed at I due to unit force applied at J. Similarly, in case of stiffness matrix, this Kij is indicating force developed at I due to unit displacement application applied at J. Okay, so this is the displacement output. Flexibility matrix are the force matrices because I am applying the forces, unit force I am applying and the corresponding displacements I am observing. Here the forces are the outputs and the force developed at I due to the unit displacement observed at J. So as I am applying a force at this action, as I am applying some force at this action, as I am applying some force, due to this force, what is happening to this end or what is happening to the top end, that is the stop condition. Or some other way, when I am giving some displacement, okay, either in the form of displacement I have applied some load, one unit displacement I have given. Due to this unit displacement, how much force is developed at A, that is the corresponding stiffness matrix. Okay, so now the output of the stiffness matrix and the flexibility matrix, we are giving a relation. So I am going for the relationship between flexibility matrix and the stiffness matrix. Okay, consider the system which is having forces P1, P2, P3 and so on Pn, and which is producing the displacements delta 1, delta 2, delta 3 and so on delta n. This delta is indicating all in all displacement. So, okay, due to the application of force in this direction, at that point what is the displacement? That is small delta. Okay, due to the application of all forces in all the directions, finally, what is the resultant displacement at 1? Due to the application of all forces, what is the final displacement at 1? That is this delta 1. Then small delta is at that particular instant. Okay, due to the force at this one, what is the displacement at this one? Due to the force at that point, what is the displacement at this point? Okay, involving all these terms, the delta output will come. Okay, involving all the force application on the coordinates, and at one coordinate, what is the displacement? Due to the application of all the coordinates on the system of the body, what is the final displacement at one coordinate? That is this capital delta, and the coordinates are 1, 2, 3 and so on n. Okay, using the principle of superposition, the definition of flexibility matrix we can write using the principle of superposition. The definition of flexibility matrix, okay, we can get like delta is equal to delta 1 1 P1, delta 2 2, delta 1 2 P2 and so on, delta 1 n Pn as delta 1 1 into P1 displacement at 1 due to P1 force at 1 plus finally displacement at 1 due to P2 force at coordinate 2. So overall total displacement at 1. Finally, what is the total displacement at 1? Firstly, displacement at 1 due to force application at 1. Next, displacement at 1 due to force application at second coordinate. Next, displacement at 1 due to force application at the third coordinate. A force of P3 is applied at the third coordinate. Similarly, displacement at 1 due to the force application at the fourth coordinate. Displacement at 1 in a summation, the overall displacement at 1 is delta. In all the things at a time. So, the overall displacement at that particular coordinate is delta 1. One coordinate has more delta. And similarly, delta 2, what it is indicating? So, the delta 2, which is equal to displacement at 2 due to a force of P1 applied at 1 plus displacement at 2 due to a force of P2 applied at 2 plus displacement at 2 due to a force of P3 applied at 3. So, in this way, we are indicating displacement at 2 due to a force of Pn applied at the coordinate n. In this way, summing up all the displacement, okay, displacement at that point due to different force applications. Displacements at this point, displacements at 2 due to the force at some other coordinate. Displacements at 2 at this due to force application some other. So, in overall summation, the overall displacement at 2 is main delta. Okay, that is delta 2. In this way, delta n we have indicated and we have given the main equation. Now, in separating it into a matrix form, we can write it as delta 1, delta 2, delta 3 and so on. Delta n is equal to delta 1, delta 2 and delta 3 and so on is equal to delta 1, 1, P1, delta 1, 2, P2 in this way. Because once you multiply delta 1, 1 plus P1 plus delta 1, 2 plus P2 plus delta 1 n plus Pn. In this way, the summations will complete. Okay, so the one line will complete. And then delta 2, 1 plus P1, delta 2, 2 plus P2 and so on, delta n plus Pn. Okay, so row wise multiplication. Matrix multiplication, you know, right? So this matrix vertical multiplication, this matrix vertical multiplication. Like that, we will take and sum up. Multiplication, 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 multiplication. So in this way, a complete single row, which is the order of this matrix. Okay, the same order of this matrix will come out, and this is a delta matrix, the total deflection matrix. This is the flexibility matrix, a delta, small delta matrix, and this is the force matrix. Okay, so in this way, the flexibility matrix equation we have got. So here, the flexibility concept. Due to the load application, what are the displacements? That is the output. Next thing, due to the displacement application, what are the forces? That is the next. Similarly, from the definition of the stiffness matrix, due to the displacement, a unit displacement application or due to the application of a delta 1 displacement, and what is the corresponding force generated at 1? Due to the corresponding force generated. Application of unit displacement, output is the force. Application of a unit displacement, output is the force. Okay. And unit displacement is applied at 1. What is the force? And unit displacement is applied at a second coordinate. What is the force generated? A unit displacement is applied at the nth coordinate. What is the force developed at 1? Okay. In this way, the force developed at 1, force developed at 2 and so on. Pn, force developed at n. In this way, we are indicating, and then again like the previous, I am separating and I can indicate P1, P2, P3 and so on. K11, K12, K1n and so on, and K21, K22 and so on, K2n, and finally I am indicating it as force matrix, stiffness matrix and delta matrix. Okay, this is from the stiffness matrix concept. Now, what I can say, substituting the value of delta from the above equation. So, starting I have got the total deflection matrix is equal to stiffness flexibility matrix into force matrix, and later I have got force matrix is equal to stiffness matrix into deflection matrix, and here this delta I can replace. Okay, this P into K into delta times P. P into K into delta times P. And this P, once you take it here, or cancellation of P and P or basic matrix conditions, you know, right? So, cancelling the P as it is, the multiplication will give the I unit matrix. Okay. So, this I matrix or the unit matrix will come, that is equal to K into delta. So, flexibility matrix into stiffness matrix is equal to unit matrix. Okay. Where I is the identity matrix or the unit matrix. In other words, the flexibility matrix and stiffness matrix are inverse in relation. Yes. So, inverse to each other. We can write that flexibility matrix and the stiffness matrix are inverse to each other, so that identity matrix has come. So, due to the multiplication of these two, identity matrix come. A into A inverse is equal to I. Right? Why? Because A and A inverse are completely inverse matrices. That's why A into A inverse is equal to I will come here also. K and delta. So, the stiffness matrix and the flexibility matrix are completely inverse in relation. Okay. So, this is the final relation between flexibility matrix and the stiffness matrix, and you should have to write this wording also. The next thing, flexibility matrix method. So, what is the method involved in the flexibility matrix analysis? So, from here our basic numerical or the concept will start. Till now it is involving all the terms we are using and the relation generated between the flexibility matrix and the stiffness matrix. Okay, in this method the basic unknowns to be determined in the analysis are the redundant forces. Yes, the P matrix is the unknown. Okay, the corresponding force, how much is the redundant force, that is the unknown. Hence, the degree of static indeterminacy of the structure is identified first. Then, the coordinate number is assigned to each redundant force in the direction. How we have done in our frame. Okay, so we should have to identify what is the redundant force, what is the unknown force. Okay, that redundant forces we need to identify. Later, we should have to give the numbering 1, 2, 3, 4 like that. Coordinate numbering we should have to assign to the each force in that particular direction. If Pi, P2, P1, P2, P3 and so on, Pn are the redundant forces in the coordinate directions 1, 2, 3 and 4 and so on respectively, and the restraints in all the redundants will be removed. So, as we have said, those are the restraints, those are the redundant forces, those in all the coordinate systems, those should be released, and the resulting structure we call it as statically determinate, because indeterminate, in which locations the indeterminacy is there, I am releasing. For an indeterminate structure, okay, for an indeterminate structure, at which locations I am feeling the redundancy, that I am releasing. So, what it is becoming? It is becoming like a simply determinate structure or released structure. Okay, so this will becoming a basic determinate structure or the released structure. From the principle of superposition, the net displacement at any point in a statically determinate structure is the sum of the displacements of the basic determinate structure due to the applied load and the redundant forces. As you already know, this is the summation happening, and this delta 1 is equal to delta 1 due to the load application and these things from the normal concept. So, due to a load of P1 is applied at 1 due to the corresponding displacement, and okay, so what is the overall displacement happening at this structure? Maybe an overall displacement is happening at this structure. How much is the when you want to calculate the total displacement at that point, that the structure, the original structure it means the total displacement generated at that point due to the given loading condition in the released structure. Okay, displacement generated at the point in the released structure plus displacements corresponding to the redundant forces on the structure. Okay, so from the principle of superposition, the net displacement at any point in the statically determinate structure is the sum of displacements in the basic determinate structure due to the applied loads and also due to the redundant forces. Okay, in this way delta 1 is equal to delta 1L, deflection due to load. Okay, these are the deflections due to the redundant forces application at the different coordinates, where delta I is indicating displacement at the ith coordinate. Okay, displacement at the ith coordinate direction, and then delta Iz is the displacement at I due to a unit force at J. Okay, in case of the flexibility matrix element. Okay, and then this delta IL is indicating displacement at I due to the given loading. L is there, that's why given load. Due to given loading in the released structure in our coordinate system, coordinate direction at I. Now, from the above equation, I can write delta is equal to delta L as the first one, and then plus delta times the P. Okay, I can separate the next matrix. And when I am keeping the P as it is, delta minus delta L divided by delta, that is P is equal to delta inverse of delta minus delta L, as this delta L is the total deflection and this is the flexibility matrix, and the P is into delta times P plus deflection due to load is the total deflection occurring. So total deflection minus deflection due to load in bracket this flexibility matrix inverse is equal to the force matrix. Okay, so the P is equal to delta inverse delta minus delta L in the determinate structure. Okay, in the determinate structure, the final displacements in delta are either 0 or the known values. In case of the determinate structure, the final displacements at the supports are completely 0, or they will be some values they will give. Okay, the solution for that from the above equation gives all the redundant forces. Then using the equations of static bending moment and shear forces required at any point may be found. Okay, so using these equations, the static moments and the bending moments and the shear forces can be calculated. So what it is saying? So this is saying the involved values of delta means the final displacements. Either these displacements will be zeros for any structure, or a known value of sinking or a known value of movement that will be known. Okay, so the remaining answers of the forces acting in the members can be calculated. The movements in the members can be calculated. Forces are the unknowns. Okay, so flexibility matrix or the force method, because the force unknowns will be calculated here. In this method is known as flexibility matrix method. Why? Since flexibility matrix is used, this method is called as force matrix because the redundant forces are the final outputs, are the basic unknowns, and then it is called as the compatibility matrix. Why? Since the compatibility conditions of the deformation in the indeterminate structure given in the final equation will be solved. Okay, so the method is known as the flexibility matrix method since the flexibility matrix is being used, and then the force method because the redundant forces are the basic unknowns. Compatibility matrix because the displacement compatibility equations I am using. Now the following steps are to be taken to get the required solution of the flexibility matrix method. Okay, determine the degree of static indeterminacy n. Degree of static indeterminacy. How I can calculate? After finding the available unknowns, after knowing the static equilibrium equations, using that the statical indeterminacy of the structure can be calculated. Next, choose the redundants. So the unknowns were the count came. In that, what are the redundants I should have to choose? Maybe in the fixed end, I have said moment may be redundant, or it may be keep it and a reaction of the prop will be redundant. So in that way, which is the redundant for you that you should have to choose. And then assign the coordinates to the redundant force and the directions. Yes. So I should have to give the corresponding direction even at the same point also. In this direction one coordinate, in this direction one coordinate, in this direction another coordinate. Like that we should have to give the numbering. And then remove the restraints to the redundant forces and get the basic determinate structure. Okay. So after removing the restraints to the redundant forces, and we should have to get the basic determinate structure. Determine the deflections in the coordinate directions to give loading conditions, in the basic determinate structure. Okay, we should have to determine the deflections in the coordinate directions due to the given loading. Whatever is the given loading is there, for that given loading, we should have to calculate the deflections. That delta L we have written, right? Okay, we should have to determine the deflections in the coordinate directions due to the given loading conditions in the basic determinate structure. Now, determine the flexibility matrix and then apply the compatibility conditions. Assign the values of delta to the computer, that is P is equal to delta inverse delta minus delta L. Knowing the redundant forces, the computer member forces will be calculated. The computer member forces. Now, for assembling the deflection, delta L is a released structure, and to assemble the flexibility matrix, we use standard methods known in the structural analysis like conjugate beam method and the unit load method. So, the conjugate beam method or the unit load method we are using in case of the matrix methods. This conjugate beam and unit load you may not know. Only simply the word itself it is having conjugate beam. So we are using the bending moment diagram as the area. Moment area method will write, right? So in the same way it will also come. So area of the bending moment diagram will be involved. In case of unit load method, removing the external load we will apply a unit load. That's why unit load method. Okay. In the strain energy concept also we have given the unit load method concept only. Okay. So assembly the deflections due to the delta L in the released structure, and also to assemble the flexibility matrix delta, we use the standard methods known in our structural analysis, which is conjugate beam and unit load method. But here we are going with conjugate beam method only for the analysis. Okay. So in this way the complete analysis will be followed. Firstly, what they are saying. So we should have to determine the statical indeterminacy, and then we should have to choose the redundants, and we should have to give the coordinate numbers to the corresponding directions, and then we should have to remove the restraints to the redundant forces and get a simply basic determinate or the released structure we should have to generate. And then for that determinate structure we should have to determine the deflections in the coordinate directions, and then determine the flexibility matrix, and then use the compatibility equation and calculate P is equal to delta inverse delta minus delta L. There the corresponding known redundant forces will be computed, and for assembly delta L is calculated in the released structure is, and also the assembling of the flexibility matrix delta also will be used. These two terms will be calculated or generated from the conjugate beam method or the unit load method. Okay. So in our classes we are going with the conjugate beam method only, right? So in the next class we are going into analyze a problem using the flexibility matrix method. Thank you.